We've covered fundamentals of chemistry in the first two lectures. Now let's go into bonding and chemical interactions in lecture 3 of our module. We'll start the lecture talking about some bonding basics. Elements in general will form bonds to attain noble gas-like electron configurations. And this is based on the octet rule, which states that in general, atoms will elect to have 8 electrons in a standard valence. There are some exceptions though. Hydrogen, helium, lithium, beryllium, and boron are stable with fewer in their valence. Elements in period 3 or greater will be stable with more than 8, and compounds with an odd number of valence electrons will not have 8 electrons on each atom. The first style of bonding we're going to talk about is ionic bonding. This is when electrons transfer from one element to another and result in an attraction based on electrostatics. This occurs between elements with large differences in electronegativities, so generally this is a metal and a nonmetal. It involves the formation of a cation and an anion, cations being positive, anions being negative. And when these things attract to each other in larger numbers, they're going to form crystalline lattices. A few things to note when we're talking about ionic bonding, though, is that they have high melting points, and they also tend to dissociate in water because water is polar. An example of this is with sodium. So if you remember from our original atoms, in the previous lecture we talked about what this looked like. Now, what's going to happen with this electron is sodium is going to want to have a full valence, and so is chlorine. So the natural result is this electron is going to go over. This is going to lead to the formation of a cationic sodium and an anionic chlorine. Because of this, there's going to be an attraction leading to the formation of sodium chloride. Covalent bonding is the other type of bonding we'll discuss. This is when electrons are shared between elements with similar electronegativities. Examples of these include a lot of organic bonding, such as carbon-carbon bonds, which are the basis for organic life. There's a few things about bond order, though, starting first with strength and energy. Triple bonds are the strongest and most energetic, double bonds being next in line, and single. Bond length, on the other hand, is the opposite. Single bonds are the longest, whereas triple bonds are the shortest. As you put more bonds in between the elements, they get closer and closer together. They also become more rigid as there are more bonds added. Nonpolar covalent bonding is when there is exactly the same electronegativity, whereas polar is when there is a significant difference in electronegativity. So, an example of a nonpolar bond would be one that's between two carbons. However, a polar one would be if there was a significant difference. So, for example, carbon-oxygen, or carbon-fluorine, even worse. Coordinate covalent bonding is when they both share electrons coming from the same element, but this is usually only found in Lewis acid-base chemistry. I drew a couple of these already, but let's talk about what a Lewis dot structure is. There's some examples below. You take the number of valence electrons for each species, add them up, and put them together. So if we were to do an example, let's do hydrogen cyanide. So if we were to look at HCN, hydrogen has 1 in their valence, carbon has 4, and nitrogen has 5. 1, 2, 3, 4, 5. So if we look at this, that's 1 plus 4 plus 5, and this results in a total of 10 valence electrons to work with. So let's go ahead and start the process out. So we've got hydrogen, carbon, and nitrogen. So that's 1, 2, 3, 4. And let's keep adding, and in general, we're going to look and we're going to want to have a full valence. Hydrogen being an exception, though. Carbon's not terribly happy with what it's got either, and neither is nitrogen. So if we were to add the rest, so we've got 6 more to work with, so 1, 2, 3, 4, 5, 6. Well, nitrogen's happy, but carbon's not. So that means that these are going to have to shift over. So now we've got full valencies. Now, if we were to add the bonding structures, let's convert these bonds into actual diagram lengths. And there we go. HCN. You will see Lewis dot structures on the MCAT, so make sure you know how to do this. To the right are some examples of other Lewis dot structures. It's in your best interest to practice drawing these for the future. Formal charge occurs when elements have more or less electrons than neutral, and the equation for which is listed below. Let's go through an example. How about we do NH4 plus? So if I were to do NH4 plus, and I'll go ahead and draw that out. NH4 plus, and this has a positive charge on it. So let's talk about calculating the formal charge on the nitrogen. So V stands for the normal number of electrons in the atom's valence shell. For nitrogen, it's going to be 5, and then you subtract the electrons that are non-bonding. Now, if you look, there are no electrons on nitrogen that are non-bonding, so this is going to be 0. And then you subtract half of the bonding electrons. In this case, there's 8. 2, 4, 6, 8. So this would be 8. And we end up with 5 minus 0 minus 4, which is going to net us plus 1. So the formal charge on the nitrogen in NH4 plus is going to be plus 1. Resonance is a variation in the electron configuration that occurs within structure. This is spontaneous and continuous, so it never stops. Because of this, it'll contribute to an overall stability in structure. Below is a diagram of SO4. As you can see, the double bond positions shift around, and this happens non-stop. This leads to an overall structure stability in SO4. Often you will see this drawn like so. So just bear that in mind. Since these double bonds are shifting around, this dotted line is to represent that. And you're going to see an overall double negative structure. So sometimes you'll see this denotation as well. When it comes to organic chemistry, resonance plays a very important role in structural stability for these organic reactions. The Sepper theory, or valence shell electron pair repulsion theory, is a three-dimensional structural theory that's based on electron repulsions. Simply stated, it makes the assumption that electron pairs will be as far apart as possible. This makes sense considering that when you compare them in a physical standpoint, same charges will repel. Non-bonding electrons often exert more repulsion because they are closer to the nucleus for this reason. There are two types of these geometries. Electronic geometry is where all electrons are positioned, whereas molecular only positions the bonding and structure. Below is a diagram of the types of shapes that you will see. In terms of polarity, this depends on the dipole moments. All polar molecules will have polar bonds for this reason. The arrow that you see in this diagram points to the electron density. So if you were to look, where the arrow is pointing is going to be where the negative is. So for example, if we were to look at HCl, this would be net positive and a net negative. Sigma and pi bonding are the two types of bonds that you will see in chemistry. And when you look at what they are, it's quite simple. Sigma bonds are when there is a head-to-head overlap. So a head-to-head overlap is going to look something like this. So if you were to look, if I were to have two orbitals and they were lined up favorably, they would overlap such that there would be a formation of a bond. Now obviously, if these weren't lined up favorably, you would see non-bonding. But if they do bond, this is what you'll see. This is a direct head-to-head overlap between these two. Pi bonding, on the other hand, is the overlap of parallel electron clouds. So again, if they're lined up nicely, the interaction is like so. When you have multiple bonds, so double or triple bonds, you're going to have one sigma bond followed by pi bonds subsequently. So if you've got a single bond like such, that's simply one sigma bond. A double bond is going to be a sigma bond and a pi bond, and a triple bond is going to be a sigma bond and two pi bonds. So you'll have one pi bond that's protruding, like so, and then another one that's going up and down. I know visually this is a little difficult to understand, but think of it as a straight across and a X shape going up and down these. Orbital hybridization is something that happens generally between sigma and pi orbitals. There's sp, sp2, and sp3. As you would guess, as you add more p's, the s character declines, so from a 50-50 and so on. For the purpose of the MCAT, you can generally simplify this expression by simply stating that sp3 is noted in alkanes, or single bonds, sp2 is in doubles, and sp is in triples. Now that we've covered the bonding aspect of this lecture, let's go into some intermolecular forces. Intermolecular forces are defined as electrostatic interactions between molecules. So this isn't within structure, this is between molecules, so it's not an individualized thing. So it's not like a dipole. But dipoles that are created in atoms are going to create effects. The strength of these forces is listed below. So the strongest being ionic forces. This is because of the electrostatic interactions. Covalent forces are next. This is because electrons are shared. And lastly, intermolecular forces, which are the weakest of the bunch. Let's talk about some types of intermolecular forces. London dispersion, or as it's sometimes called, van der Waals forces, are the weakest of these intermolecular forces. This is the spontaneous formations of dipoles within structures. This happens because the electrons will always fluctuate in structure. Because of this, you'll often see dipoles forming for very short periods of time, causing very, very weak electrostatic interactions between molecules. Note that London dispersion is present in any molecular solution. Dipole-dipoles are when there's an attraction between oppositely charged dipoles. This is obviously stronger than London dispersion forces. The most common example of this is water. So if you're to look at water, you're going to see a negative moment here because you've got a dipole moment. Well, this is going to be attracted to the hydrogens here. So this is technically a dipole-dipole moment, but as you would guess, this is more like hydrogen bonding, which is what we're going to go into next. This is a type of dipole-dipole interaction. This is bonding between hydrogen and electronegative atoms. So in this case, for the purpose of water, you've got oxygen and hydrogen. This is unusually strong, and because of hydrogen bonding, you're going to see differences in boiling point and melting point. For the purpose of the MCAT, you will be asked to discern which compounds have higher boiling points. And take note that hydrogen bonding contributes largely to these boiling points. More hydrogen bonding is going to create a higher boiling point. One thing that students get trapped on is that they think hydrogen bonding is its own separate thing. Remember that hydrogen bonding is a type of dipole-dipole interaction, which is why I drew it in between the two. Alright, so we're going to finish up there when we're talking with our discussion of bonding and chemical interactions. In the next lecture, we're going to go into some calculations when it comes to compounds and stoichiometry. We'll see you then.